This video summarizes the achievements of the second scale-up of the proposed use cases within a RISE EU project at POLIMI TEF. Let's begin with Challenge 7. The goal here is to streamline the PCB desoldering and reworking process. The workflow connects two distinct stations: a control station for identifying defects and a reworking station where the robot assists the human. The primary goal is to minimize the operator's setup time by introducing a collaborative workflow between these two stations. For the second scale-up, we developed a unified persistent data management system relying on ARISE toolsets. The architecture utilizes ROS2 and VulcanXS for high-frequency tasks, while the FIWARE Orion LD context broker acts as the central state manager. This design separates data producers, like the robot and camera, from data consumers, such as dashboards and history loggers. At the control station, a dedicated GUI identifies defective PCBs. It uses a YOLO model trained to identify electronic components, displaying annotated images with bounding boxes. Because the context broker is optimized for metadata, we employ a fast API server to handle heavy image payloads. The metadata is then forwarded to the reworking station. Here, the operator monitors the robot status via dashboard connected to the UR5E robot's OPC-UA server. The system translates these readings into NGSILD attributes, allowing for historical performance analysis through Grafana. While cobot prepares the workspace for the operator using transmitted data, the automated guided vehicle is moving towards the reworking station and upon its arrival informs the cobot for unloading the boards for the operator. In this way, the workspace and the workpiece have already been set for the operator to start his dismantling task. We now move to Challenge 8, HRI for improving ergonomics in high-precision tasks. This use case features an assistive holder scenario where a collaborative robot adjusts its end effector to satisfy operator well-being while performing dismantling tasks. This monitoring system uses 3 Intel RealSense cameras to capture the operator's posture from the front, left, and right angles. This system incorporates 3 primary functionalities: operator posture assessment, LLM-based interaction, and data recording. The architecture integrates AlphaPose for human pose estimation and a ruler calculation module. Data is managed through the ARISE middleware. The graphical user interface visualizes the pose estimation. It provides feedback using a color-coded system, green for good posture and red indicating a need for immediate improvement, allowing for real-time ergonomic monitoring. A key achievement here is the human cobot communication system. The operator can control the robot using natural language. The operator's voice is processed by a Whisper model for transcription and then analyzed by the Llama 3.2 large language model to identify the intent. This triggers the robot to adjust its position, ensuring the operator maintains an ergonomic posture during the task. On the right, the architecture captures operator pose and calculates ruler scores using ROS2, transmitting data to the Orion LD context broker. This persists the information in timescale dB, which feeds the Grafana dashboard on the left for historical ergonomic monitoring, allowing us to identify specific moments of poor posture during the workflow.